series and parallel circuits. Get ready for a very quick review. Series circuit. Series circuit is where the elements are connected one right after the other in a single path. There's only one path for current to flow within a series circuit, and therefore one of the problems with a series circuit is if one of the elements, like this light bulb, burns out and breaks open the circuit, then no current will flow because there was only one path and now the path has been broken, and that's called an open circuit. Because there's only one path for current to flow, the current has to be the same everywhere in this circuit. So the current here, it's easy to flow through a conductor here. There's no potential difference in a conductor, so there's really no work necessary to move the charge from one point to another. The work is done across these resistive elements to pull the charge off or out of these sticky atoms here. And the amount of difficulty is proportional to the amount of resistance here. So the higher the resistance, the more work is necessary across a particular resistor, and so therefore this resistor is the more limiting factor, although they both play a role in limiting the amount of current flowing in this circuit. Because both resistors play a role, if we're going to try to find out the equivalent or total resistance in a series circuit, remember that since the charge has to flow through both of these resistive elements and there is no resistance in the good conductors here, the total resistance is quite simply the sum of these two resistances. So in this case 2 plus 4 is 6 ohms. So the battery, in this case the source, if it doesn't know what it's connected to here, would assume it's connected to equivalent resistance of 6 ohms. In this case with 3 resistors, you would add all 3 and get 370 ohms resistance that the charge had to move through to go from one side of the source to the other. And that's how you find equivalent resistance in series. You add them up. Now, once you've found the equivalent resistance in series, we can find the total current flowing in a circuit because we can use Ohm's law. Our amount of work per charge is 12 volts here, and we're doing work to push the charge and pull the charge through 6 ohms of resistance. So I equals V over R, and we get 2 amperes flowing. Notice that if we put an ammeter in series here, we get 2 amperes flowing here, we'd get 2 amperes flowing here, 2 amperes flowing there, because the current in series has to be the same everywhere. Now, to do a whole problem with a series circuit, we're going to use those ideas that we just talked about here, and we're going to also find the voltage drops across these resistors here. Because the current's the same everywhere, we can start off by finding the total current in this circuit after we've found the equivalent resistance here. So the equivalent resistance is 45 ohms, and since we have 9 volts of push and pull, divided by 45 ohms gives us a current of 0.2 amperes. Now once we know how much current's flowing in each of these resistors, since it's the same, we can use Ohm's law to find out the voltage drops across these two resistors. And our first voltage drop, therefore, is 0.2 times 15 ohms is 3 volts across this 15 ohm resistor. So our voltmeter, which we put in parallel here, would read 3 volts. And then if we have a voltmeter put across this second resistor of 30 ohms, 0.2 times 30 is 6 volts across this resistor. Notice that it makes sense that you'd have 6 volts across 30 ohms and 3 volts across 15 ohms because it takes twice the amount of work to move the charge through twice the resistance. And we only had 9 volts, so these two voltage drops, V1 and V2, have to add up to what we began with. And that's known as Kirchhoff's voltage law. The sum of the voltage around any loop in a circuit is equal to 0. So 6 volts plus 3 volts in one direction is equal to 9 volts in the other direction. For example, when we look at this here, we have 9 volts where this is positive and that is negative. This voltage across this 15 ohm resistor is positive on this side and negative on that side, which is opposing this. And this voltage is positive here and negative here. So we have 9 volts, but then we drop 3 volts and we have 6 volts left over. So by the time we get back to our source, we have no volts left over. We've done all of our work. And that again is Kirchhoff's voltage law. And that was our quick review of series circuits. So now we're going to go right into parallel circuits and our parallel circuit review. Parallel circuits are where the elements are lined up in parallel. That's the structure that it is visual here, and therefore the source is connected to all of the elements on either side of the elements, and we have what are called branches. So the current comes in and branches into multiple paths here. So there are multiple paths in a parallel circuit with multiple branches, and the good thing about that is that if one of the paths is not used or one of them is broken and we have an open circuit, then the other paths still conduct current and are still functional. And your house is wired in parallel because everywhere you plug in, you want to be plugging in to the source voltage. So the big key in parallel circuits is that the source voltage is the same everywhere in the circuit, because all of the resistors or all of the elements are connected directly back to the source through conductors. The voltage drops across every branch are all equal. So if we have 12 volt source, we have 12 volts dropped across each of these resistors. So let's go ahead and take a look at a parallel circuit here and how we would analyze this circuit. And typically we would know the source voltage and we know the value of each of these resistive elements. And so in this particular case, the first thing always is to recognize that the voltage is the same everywhere across each element in a parallel circuit. Now, because the voltages are the same, we're going to get, if we have different resistances, we're going to get different branch currents here. And the total current feeding into these is going to split based on the amount of resistance here. So using Ohm's law, we can find each of these branch currents. We can find the current flowing through R1 here, V1 over R1, and we get 4 amperes. And then we can also get the current flowing through resistor 2 here. 12 volts divided by 6 ohms is 2 amperes. Notice that that should make sense. Since the voltage is the same and this is twice the resistance, this should be half of the current compared to this current coming in. Now, the total current coming in has to feed both of these branches, and so the total current is the sum of all the branch currents. So 4 plus 2 is 6 amperes. So in series circuits, we had the same current with different voltage drops, and the voltage drops added up to the source voltage. In a parallel circuit here, we have the same voltage. We have different branch currents that add up to the total current coming in. So there's kind of an idea of duality between series and parallel circuits here. Now, our next step is we could find out what the equivalent resistance is that this source feels when it's attached to these two resistors in parallel. And we can use, the easiest way to do that is to use Ohm's law. If you know the total current and you know the total voltage here, we could find out what the equivalent resistance is by just taking the source voltage divided by the total current of 6 amperes and getting 2 ohms. So the source here would feel like it was connected to 2 ohms. It wouldn't necessarily know that it was a 3 ohm resistor in parallel with a 6 ohm resistor. Notice that the equivalent resistance is always less than the smallest resistor. If you could imagine without this resistor in the circuit and we just had a 3 ohm resistor. When we add another resistor in parallel, it really is like opening another lane for current to flow. Therefore, when we add resistors in parallel, it increases the amount of current flow and decreases the equivalent resistance. Therefore, it's always going to be, the equivalent resistance is always going to be smaller than your smallest resistor in the circuit. Another way to find total resistance or equivalent resistance in parallel is to use our products over the sums equation here. That one can only be used if you have two resistors. If you have more than two resistors in parallel, you have to use our inverse or ratio equation down here. Using the products over the sums in our circuit that we were just analyzing here with 3 ohms and 6 ohms, if you multiply 3 times 6, you get 18 ohms squared over 3 plus 6, 9 ohms, and we would still end up with 2 ohms like we got previously by using Ohm's law. But if you don't know the power source, you wouldn't be able to use Ohm's law, so this is how you would find the equivalent resistance in parallel. If you have more than 3 resistors in parallel, you have to use this equation right here. 1 divided by R equivalent is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and so forth. Using it in this case, we just have 2 resistors, we can still use it. 1 over 3 ohms plus 1 over 6 ohms is equal to 0.5 over ohms, because 1/3 plus 1/6 is 0.5. And therefore, then the hard part of about this equation is once you've added these two fractions together, you have to then take the inverse, hit the 1 over x key on your calculator to find out the equivalent resistance. You can't leave it in this form because that's 1 over R equivalent. You have to hit the 1 over x button or x to the -1 button on your calculator to get the equivalent resistance here. So 1 divided by 0.5 over ohms is 2 ohms. So it's a little bit clumsy, but this is what you want to use if you have 3 or more resistors in parallel. So now, calculating everything in a parallel circuit here. And here's our overall circuit. What we know, and we always start off with parallel circuits, is the voltage is the same everywhere. And in this particular case, we also know what the input current is here, 10 amps. So that's also the current flowing out. And that 10 amps has to branch into these 2 branches. We also notice that we know that we have R1 is 40 ohms. So we can find out this branch current, I1, through this ammeter, which is in series, where the current's going through it. And so finding I1 here, 120 volts divided by 40 ohms is 3 amperes flowing this way. Well, if I have 10 amperes flowing in and 3 amps flows this way, then I must have 7 amperes flowing this way. So I2 must be equal to 7 amperes, because 10 is equal to 3 amps plus I2. So now that I know the 2 branch currents here, the last thing to do would be to find out what the equivalent resistance is. So, or the resistor R2 is, and then we can find the equivalent resistance. So the R2, the resistor R2 here, we know that it's 120 volts across this resistor and 7 amps flowing through it. So we can find out that its resistance is 17 ohms. And then our equivalent resistance is the total voltage divided by the total current, and that ends up being 12 ohms. Notice that 12 is less than 40 or 17 here. So we should feel pretty good about that. We could have also done our products over the sums here, taken 17 times 40 and divided by 57 and ended up with 12 ohms also. And like Scratch says here, wow, that was a lot. Scratch's parting idea. And you really are at the beginning of your quest for continuous improvement.